Chapter 12 Atmospheric Hydrology, Section 12.6 Evaporation and Transpiration. So water is removed from the Earth's surface and returned to the atmosphere by two processes. Evaporation, which can be defined as the process where liquid water is transformed into a gaseous state. Remember, evaporation can only occur when water is available. There's way more evaporation taking place over moist surfaces or water bodies than there is over land. The other process that moves water to the atmosphere involves plants, and that's transpiration. Let's talk a little bit more about evaporation. Evaporation also requires the humidity of the atmosphere to be less than the evaporating surface. Moist surface cannot evaporate into an atmosphere that has 100% relative humidity. And the rate of movement of water from that moist surface to the atmosphere is a function of humidity, and it increases greatly as the humidity gets drier, because that means the atmosphere has a much greater ability to hold moisture. Evaporation also requires large amounts of energy, so we should expect that evaporation as a process globally is much stronger in the tropics and subtropics than it is in the middle or high latitudes. To evaporate 1 gram of water requires 600 calories of heat energy. Now back to plants. So plants move water through their bodies, and that water originates from the ground, is picked up by the roots, moves through the stem, and then is lost through the leaves through openings called stomata. So stomata are small openings. They're connected to the vascular tissues that exist inside a plant. And for most plants, this is a passive process. The stomata are always open. They don't close. Some plants do have the ability to close their stomata and therefore control the loss of moisture from their surfaces. Now, the movement of this water from the ground through the plant's roots, stems, and leaves is a very important process. One, when it gets to the leaves, it helps keep the plant cool. Evaporation requires heat energy, so the plant will not overheat. Plants don't do well when temperatures are too high. It starts destroying the contents of the cells. So they want to stay cool, so they move a lot of water. And water movement through roots to stems to leaves also moves nutrients to where they're needed in the leaves, where active photosynthesis is taking place. For most plants, transpiration is controlled by the humidity of the atmosphere and by the amount of moisture in the soil. If you run out of moisture, you can't transpire anymore. And if the atmosphere is saturated with water, very little transpiration will take place. So here's a stomata, a close-up picture of it. Quite a scary looking thing. Of the transpired water passing through a plant, only 1% is used in the growth process. So that is incorporated into cells. So as I said, transpiration also transports nutrients from the soil to the roots, and then carries them up to the various cells in the plant through the stems, if there's stems. It also is important transpiration from stopping the plant from becoming overheated. Scientists, from a scientific perspective, we treat evaporation and transpiration as separate processes. But when we try to measure these two in the field, we combine it. It's very, very hard to separate those two processes in a forest or in a grassland. So we use a composite term called evapotranspiration. The rate of evapotranspiration at any instance from the Earth's surface is controlled by 4 factors. The amount of energy to convert solid water to liquid and liquid to gas requires a lot of energy. We need a humidity gradient away from the surface. Humidity needs to be low in the atmosphere in order for it to receive moisture. Wind speed is a very important process in evapotranspiration because wind speed brings new sources of dry air to the plants that are doing the evapotranspiration or the ecosystems. And of course, water availability. If there's no water in the ground, evapotranspiration is not going to take place. So the following two maps show the difference between precipitation and evapotranspiration on the Earth's surface. So where the colors are sort of beige, yellow, orange, then brown, that is where there's more evapotranspiration taking place than precipitation. These are major sources of water for the atmosphere. And then light green to dark green indicates areas where precipitation is higher than evapotranspiration. So we can see in here how the subtropics, high temperatures, over the oceans, a lot of water is being evaporated and entering the atmosphere. Precipitation is higher than evapotranspiration in the tropics, where the intertropical convergence zone is, and in the mid-latitudes. And you can see the high amount for January just off of BC coast and Oregon and Washington State and into the Pacific Ocean. Mid-latitude cyclones are producing that precipitation. And then off from the east coast of Canada, we can see a band of more precipitation than evapotranspiration taking place. Okay, so this first map represents January. Let's now look at July. And what we should see in July in the Northern Hemisphere, the North American continent dries out somewhat, and the intertropical convergence zone where it produces this precipitation moves northward. There's going to be a shrinking of the high pressure systems in the Northern Hemisphere, and a shift in the location of the high pressure systems and areas of high evapotranspiration in the Southern Hemisphere. And you can see on here, once again, some precipitation hotspots. So Pacific Ocean from northern Pacific in the center of it to Alaska. There's a band across northern Canada, and then extending out from the eastern side of North America all the way into the Arctic Ocean. High levels of precipitation in Central America, intertropical convergence zone, thunderstorms and hurricanes in southeastern United States. And you can see the monsoonal effects in July. You can see how much precipitation is occurring in India and Southeast Asia.